Okay, I could start again, but it says my screen sharing is paused. I'm not sure what I need to do there.
Maybe you can stop sharing and try it again.
Okay, stop share. Doesn't want to do that either.
Yeah,
Is it
now
working?
it works. Yeah, now it works.
Okay, shall I begin?
Yes, yes. So now we
Okay,
start the second section.
okay. So, formalized mathematics. What can we do here? So answering your question, Laura. So why do math by machine? Certainly these days, there are a number of well-known proofs, claims of conjectures that are disputed. So it would be nice if we could validate these by machine. It's not a very practical option at the moment, but it is certainly a potential motivation. Often when we look at existing proofs, we see hidden assumptions. One can see the formalization of mathematics as creating a body of formal code which can be analyzed in various ways. And we could imagine taking the great body of mathematics done for centuries and somehow putting it on a common framework in a searchable format and so on. But a really important motivation is the fallibility of mathematics. So this, I can't remember where I found this, but it's wonderful. This is a single page of a book. And as you can see, there are a lot of things that really didn't work very well for people. And so this kind of thing keeps happening. There was this little story here about the Hilbert's collected works that had to be corrected by Olga Palsky, who spent 3 years repairing the errors in Hilbert's proofs. And Hilbert, of course, is not a student. So this is a situation that is not very suitable. Now, of course, Voevodsky really put this question on the map. I don't at all understand what kind of work he did, but clearly he had made a serious error that upset him very much and really undermined his confidence in his ability to continue working. So there is certainly a motivation for doing this if we can. It's just not so easy to do. Now, first we could look at, shall you say, intrinsic obstacles to formalization. And there are some well-known complaints. The wonderful claim that it took 362 pages to prove that 1 + 1 = 2. Actually, they didn't even do that. So if you take down your copy of Principia Mathematica, which is available in a very convenient paperback form, and it's a very interesting book to own, actually, what they proved was some kind of property of sets, which is equivalent to 1 + 1 = 2 once you make the necessary definitions. Well, we are not doing it the way they did, so this is not a problem. Of course, there is the suggestion of Gödel that Gödel's incompleteness theorem makes the whole enterprise impossible. Now, this rests on a big misunderstanding. Now, I am really puzzled because Adrian Matthias, who is a logician and should know better, was making this point. But mathematics today is done axiomatically. So it might be said in the 19th century, mathematicians would put things in proofs that hadn't really come from any written down kind of reason. And this is how they started using things like the axiom of choice without even understanding that they were doing it. But mathematics today is much more closely tied to axiomatic foundations, even if they're not confessed explicitly. So any incompleteness that would arise from Gödel's incompleteness theorem would already affect mathematics, whether or not it is formalized. So we, in formalizing mathematics, are not introducing a further limitation that was not already present in any axiomatic mathematics. Finally, the fact that first-order logic is undecidable, so you cannot make a machine that will prove things automatically. Now, in fact, you could turn it around because first-order logic is complete. And in principle, anything that is a theorem can be proved if you wait long enough. Completeness is one of those theoretical properties that turns out to be completely useless in practice because waiting 10 to the 27 years is not of any good to any of us. So we are not trying to completely automate mathematics. And I think in the best sense of computer science more generally, and in AI more generally, we don't want to replace people. We like people. People are good. We just want to help people. But there are serious difficulties in formalizing mathematics. They're just not the difficulties shown on this slide. Here is one difficulty. Now, the difficulty of definedness is, in my opinion, not that serious, but it certainly is aggravating to some people. So this difficulty is simply that many things in mathematics are not defined everywhere. So 1 divided by 0, what is it? Well, in Isabelle, division by 0 gives you 0, in fact. Now, this can cause a general freak out. Nevertheless, it doesn't actually cause any difficulties in practice. If you like, it's a philosophical approach of whether you care that we have chosen to extend the domain of definition of something that was left undefined for our convenience. But even if you don't say that division by 0 equals 0, you can say, we're not going to tell you what it is, but whatever it is a actual real number. So it's not some magic extra thing. And in particular, it equals itself. So this is a very simple approach to take, and it actually goes pretty far. What else can you do? Well, as mentioned in the previous talk, you can use dependent types to specify the domain of definition of the function and ensure that it is used only when applied to a value that satisfies any necessary properties. So in the case of division, you can then require that the divisor is non-zero. So that works. There are formalisms called free logics where you reason explicitly about the property of being defined. So you introduce a predicate, defined, which can be applied to any entity and tells you whether it's defined. In my own opinion, a free logic is not worth the extra complexity. In free logic, here, division by 0, in fact, first of all, we know it is not defined. And secondly, identities between things that are not defined are always false. Which then gives us, if you like, this not equals cannot also be false because we'd have a contradiction. So it's true and doesn't appeal to me, but people have their preferences. This, as I said, is a minor problem. A more serious problem is the problem of legibility of notation. So when you look at any mathematical text, you will see things like this. These are massively overloaded in their meaning. So function applied to x. image of X. So now this X is little x, we assume is a real number because it's little x. That X is a big X, so we assume it's a set, maybe a set of reals. But if it were a big N, we maybe would assume it was a set of integers. And now this is an image. This is an inverse image. This is the inverse of X times Y. But F, because it's called F rather than X, we decided is a function, and this is the inverse of a function. This is the inverse of the sine function. But this, suddenly we're raising the thing to the second power. So all these notations here, this thing, nothing is being raised to a power. We're applying an operator twice, and this D isn't really even a normal function. It's a kind of operator with weird properties, and on and on and on. So we have, and of course, people love these notations. I note in talking to mathematicians that they don't want to give up this kind of syntax, which you can use. So in a computer algebra system, they preserve a lot of these notations beautifully and they can cope with them. Whereas when we formalize proofs, it usually looks pretty horrible. So this is Hall light. This proof is not a very interesting proof, but that's code, right? This is code. No one will ever be able to read this. And this is a very short proof, by the way. So as I say in my remark, there are proofs in Hall light which are 50 times the length of that. They go on pages and pages. They are absolutely impossible to read. No one should try to. We can do better. So this is Isabel, which is, of course, the system that I use, by having the notion of a structured proof. The key element of a structured proof is that we have assertions inside. So if I can go back here, mostly we just have code. So this code says, do this, do that, do the other, and it keeps doing stuff until eventually the theorem is proved. Whereas here we say, that's what I'm trying to prove at the top. This is about shifting a path along. Never mind what this does. But here we do some stuff, and you can see that to prove this original thing we set out to prove, we have to prove something else. Never mind exactly what it means, but we can read what it says. We need to show this fact, path of shift path, etc. And we've written it out so that someone who has lost track of how they got there can say, I've got to prove this. I've got to prove that. And you see, this is just some inequality. This is some a disjunction of facts about X and Y. I've got to prove this. So by writing out the structure explicitly and by repeating at every level what we are required to prove, we have a much clearer structure, and so we can have a much better chance of reading it. So that's an improvement. We still cannot claim that this is truly legible, however. So I would like to go and just list some of the mathematics that's been formalized in Isabel. I'm not going to talk about them. I'm just going to list them. There's quite a lot. Incidentally, the blues are theorems, the greens are theories. So these are like bodies of results. And there's really quite a lot of stuff. So, and I should say, by the way, a lot of the stuff in the blue was stolen from Hall light. So John Harrison proved all these in Hall light, also using simple type theory. These in Isabel are using type classes. A lot of the things on the right side were done by various people. And a lot of this is some very advanced mathematical developments. So you can certainly, it's possible to formalize mathematics. And listing some of these, so this famous fly speck project, which was one of the earliest cases. In fact, these first two, the fly speck project and the four-color theorem, were examples of using formalization to confirm a disputed result. So the four-color theorem relied on a lot of code. A lot of people didn't like the proof. Now, I think today it is probably still true that people do not like the proof because it involves a huge case analysis, but at least they can have much more confidence in the code because it was replaced by code within the Koch theorem prover by Gontier. And our confidence in this code is massively improved because it was formally verified within Koch. A very similar situation with regard to the Kepler conjecture, which is about filling space with spheres. This was a very big project using a lot of people. Then there was the odd order theorem of group theory, formalized in Koch by a big team. And if I can plug my own work, Gödel's constructible universe and both incompleteness theorems. And by the way, a group in Uruguay has recently formalized forcing using the same setup as I used to do Gödel's constructible universe. Forcing has also been done in Lean. So an awful lot of really quite sophisticated mathematics has been formalized already. Now, there have been criticisms. So again, Kevin Buzzard has to be our guide here. Boring, he says. 19th century elementary first year mathematics. That is not quite true and it is not quite fair. Nevertheless, allowed me to quote him. His complaint is that much of what we have formalized is very long proofs about simple objects. So I italicize this. He wants to see complexity of very, very sophisticated mathematical constructions that take pages and pages and pages of definitions just to define the thing, let alone to prove anything about it. Okay, so that's where we are as regard the state of formalization. I would like to state what I think is the biggest obstacle, proving the obvious. Now, I assume we all know about the mutilated chessboard, right? Everyone's heard of this. The fact that it is trivially impossible to cover this mutilated chessboard, that is with the corners cut off, so to cover the rest of the chessboard with dominoes, as we can see by a coloring argument, because there are more gray squares than blue ones, so trivial, right? You could claim that this is artificial, so it doesn't really count. But in real mathematical proofs, obvious arguments stymie us. They cause problems every time. So in any number of combinatorial proofs that involve taking colored balls out of bags or replacing them or not replacing them, you're facing a nightmare to formalize this. A lot of commuting diagram arguments. If you know complex analysis, they draw a little picture, they draw a little circle around the origin. A winding number is obviously 1. Well, if it's literally a circle, it's trivial, but very often it's a bunch of things connected together. And suddenly to prove that the winding number is 1, although it's obvious from the picture, is a massive amount of work to do it formally. Or things like the cancellation of poles is another one. I have a particular example that bugged me a while back. So here's a very simple mathematical statement. Let f be a differentiable function, or rather it's differentiable at some point z. And suppose we have a convergent series of real numbers going to 0. Then what we would like to know is that the derivative of f at z is equal to this. And your first thing you're going to say is, that's the definition of a derivative, isn't it? Well, not exactly, because the definition of a derivative is to put some arbitrary sequence here that converges to 0, not a particular one. And you might think, well, can't you just plug it in? And it certainly looks like you should be able to plug it in. Certainly, I spent a week or more thinking, surely this just follows from the definition trivially. I asked people and so on. And the only reply I got was epsilon and delta are your friends. So this staggeringly simple looking thing was 32 lines to formalize. That's just one example, but I want to show you 3 more trivial proofs from a textbook on a number theory by Paulson. That's the first one. Now, you don't need to know what an elliptic function is. It's just notice this is a 1-line proof, trivial, right? Until you formalize it and it's 60 lines. These are all taken from the same page, by the way. So now the next theorem, there's your proof. They just cancel out trivial. That's 100 lines. And the last one, oh, you just apply this theorem and then apply the other theorem. It's trivial, right? So what have we got here? We have got nearly 400 lines of formal proofs to prove what was 3 sentences in a textbook. And this is chapter 1 of the textbook, by the way. So we have got a problem, and I'm not really sure. So when I see other authors writing about formalizing mathematics and about, for example, writing automatic systems that are going to do this, I honestly don't see how in any foreseeable future we are going to make a program that is going to read this sentence and figure out the whole proof. I think in the case of Cauchy's residue theorem, there are a lot of further complications that all he's doing here, these are not proofs at all. They are just hints as to how you could actually prove it. Okay, well, that was, if you like, the negative, the complaints, but what have we done? I'm speaking here largely about our own project at Cambridge, funded by the EU. So this, I will have a few slides on this so-called ordinal partition relations, if I may. This notation was introduced by Erdős. The idea is to generalize Ramsey's theorem. So here we're talking about n-element sets. So this bracket AN is the set of all n-element subsets, if you like, of A. And the idea now is to take an ordinal alpha, take its n-element subjects, and we talk about coloring. So instead of partitioning, we just say, oh, you just colored the sets. You color them red or black, or you color them simply 0 or 1. So this statement here, alpha, ara, beta, or gamma n, is the claim that if I have alpha and I take its n-element subjects, if I color them with 0 or 1, then either there is a set beta colored 0, or a set B colored 0, or a set C colored 1, where this is referring to the order type of a set, which is a vague concept of size. So we can think of this as indicating bigness if you're not familiar with order types. There is either a set B of size beta colored 0, or a set C of size gamma ordered 1. So in particular, if you've heard of Ramsey's theorem in the infinite case, it can be written as this little formula. So who cares about this? Well, Erdős was very interested in this. And whenever anyone says what you're doing isn't proper mathematics, I can say, well, Erdős did it. And I assume that shuts them up. It ought to. So It turns out if you consider simply the case n equals 2, so we get rid of n now, n is always 2 for us now. It turns out some of the cases of his question are trivial, like if the second order type is simply 2, then it turns out to be trivial, kind of almost by definition. As for this one in red here, this turns out to be false by a not too complicated argument. So Erdős became interested in the very simple case of countable ordinals, alpha, and simply the number 3 as the second order type. Erdős offered $1,000 of his own money to anyone who could solve this. Well, that was a safe bet because, in fact, no one has solved it. People have made progress. Work that a group of us at Cambridge recently formalized in Isabel include these instances of the partition problem that I just described. So I'm not going to go into any detail, but merely wanted to say that we have done these. They were not easy. So we have here, so I could tell Kevin Buzzard, we did some very sophisticated constructions here. It's not about the length of the proof, but the sophistication of the constructions. And we proved a number of other interesting theorems, such as this Nash-Williams partition theorem. And I would like to thank my colleagues, Mirna and Angeliki. I think Angeliki is actually here, I see there, for their assistance in this. So moving on, what else have we done? And actually there's more work by Angeliki and Wenda Lee here, as well as by my other postdoc, Anthony Borg. So I'm not going to go through these in very much detail, except to say none of this is 19th century. I think all of this is from no earlier than 1970, and some of it is later than that. So there is some quite interesting things here. So we are trying to do more and more sophisticated mathematics using Isabel and using simple type theory. A lot of this will rely on the type class mechanisms talked about in the previous hour, and some of it also using locales. I want to mention Grothendieck schemes in particular. This was a project led by Anthony Borg, and which we finished several months ago. Not in any detail, and honestly, I don't really understand how it works myself, but it is a very, very elaborate construction of things that built up from rings and adding more and more levels of things. And it's used in algebraic geometry. The reason for formalizing Grothendieck schemes was because Kevin Buzzard, who is the real name here to deal with, kind of hinted, and indeed others said, well, this is beyond simple type theory. It turns out that wasn't true. We did it only in a few months. I don't remember how long, maybe just 3 or 4 months. It took them a year, and we didn't copy their work either. We did it in a quite different way. And we also didn't have to make 3 attempts to get it done. So possibly simple type theory actually worked better here. Now, it was Anthony's choice to use locales everywhere to structure all of these very elaborate systems of definitions. And this seems to be the other issue. So I mentioned the problem of obvious proofs as an obstacle. The other problem clearly is the extreme sophistication of modern day mathematics, the levels and levels and levels and levels of definitions that they use that make it so hard even to state your theorem, let alone to prove it. So here we have been developing a locale-based approach for talking about these very sophisticated constructions. Now, I finally want to say a few words about what locales actually are. So just to remind you, this is not an extension of the logical formalism. This is part of the theorem prover. So I've said already, we have already in 1940, specifications were represented by predicates, which in fact Church and Russell called classes, and which now we like to call sets. So locales are a way of writing a predicate in a pleasant form that you can nest them, you can combine them with other locales, and you can get a proof context in which you can build a proof. And when you build locales upon other locales, and that is combining them with the previous predicates with a nice notation and with a system that unwinds all the definitions in a more or less intuitive way. So in particular, we have what appears to be a kind of even multiple inheritance where you can define constructions and then combine them again. So you can build separate branches and combine them again. So how did it work in the Grothendieck scheme example? I just have a few of them here. So this was one of the things from the Grothendieck construction. I don't actually know what this really means. This seems to be about a set U being covered. The cover is given here as a thing. It's indexed by reals. So it's some arbitrary set that is indexed by reals. And so index is the index set. And so locale cover of subset is internally a predicate taking as arguments these four things, that is X, U, index, and cover, and the predicate is equivalent to the conjunction of the assumptions there. Oh, sorry, I did too many. Let me go back. Now we can combine cover of subset, specifying the four parameters, and combine it with a locale for topological spaces to talk about an open cover. And the only further assumption is that the elements of the cover are open sets. So here we have defined a new predicate taking these four arguments. I see is open comes from topological space. And is introducing this further. Effectively, it is an axiom, but logically, it is just a predicate expressing this property and conjoined to that predicate up there. And we do it some more. So here we take the previous locale and introduce. See, it's got the same arguments as before. X is open, U, I, C, and is assuming that U is itself also open. And you just go on and on and on and on and on. Some of these get very long, and I need to say, so just to be fair and reasonable here, the argument lists get extremely long, and one of the things we need is a way of bundling up these arguments that behaves well. Okay, I want to change the subject slightly and think about what mathematicians have said when they ask what kind of assistance they want from computers. So, for example, Harvey Friedman, who has expressed himself on the mailing list called Foundations of Mathematics, he would like something based on set theory. He would like some kind of intuitive notion of types somehow supported by set theory, and he certainly wants to use mathematical notation. He wants to have a clear notion of definedness so that 1/0 is definitely not defined and can't be written. That's one point of view. Now, De Bruijn, and of course, Friedman and De Bruijn are both absolutely mathematicians, or they all are actually. All of these people here, they're all professional working mathematicians. De Bruyne absolutely hated set theory. I know I had the privilege of talking to him on a number of occasions. His hatred and disgust with set theory is really quite impressive. So for him, and he's written very eloquently about this, all of mathematics is typed. So a line is not a set of points and so on. And he, of course, built a system based around a dependent typed calculus, his automath languages, and classical mathematics. For him, the question of definedness was dealt with using his automath language dealt very well with that, using effectively a kind of propositions as types thing. And he already introduced the irrelevance of proof idea back in 1968 or so. For Tim Gowers, Fields medalist, I think Friedman must also be a Fields medalist. He wants it automatic without search. I don't know how you're going to do that. He wants to write everything in natural language. So presumably one would like to write something that looked a little bit like the textbook I had just complained about, and have a system in the background that is smart enough to be able to fill in all the gaps. I think he once incautiously said he wanted it to be as smart as a graduate student. I'm not quite sure. That betrays a certain view of graduate students. This is not going to happen in any of our lifetimes, I think. Now, what about Kevin Buzzard? And one could say Vivaldi before him. So Vivaldi, of course, was a professional mathematician, I think also a Fields medalist. And he was one of the driving forces behind the homotopy type theory work, which is, as I understand it, based on Martin-Löf type theory with models that come from the world of homotopies, which of course I know very little about, but gave you some meaning to the use of identity and equality in type theory. So potentially very interesting work, which, however, has not yet made an impact on the actual formalization of mathematics, as far as I know. Now, where the real action has been happening, apart from our own wonderful group, of course, is Kevin Buzzard, who has been able to really energize the mathematical world, not only his own students, I think, but many mathematicians around the world. They are formalizing tons and tons of things. In fact, an example I gave in a previous talk about the problem known as squaring the square, that is tiling a square with other squares of all different sizes. He had got a proof done within 24 hours. So I can't compete with that. They have quite a lot of guys doing that. So people are, so there are a lot of real mathematicians doing this now. And I'm confident that we will certainly, no field of mathematics will prove impervious to formalization, but we are going to struggle to prove some of these things, very easily. So the problems of the obvious proofs are not going away at all. I want to briefly move on to the issue of trust, because it's a fundamental issue if we're going to accept, if mathematicians are going to accept the work we do. It is well known, I think, that computer algebra systems often give wrong answers. Maybe, I don't know how many of you have used a system like Maple or Mathematica. And they're very powerful, they're very useful, they're widely used, they are ridiculously expensive, but they often are unaware of singularities, so they often make assumptions they shouldn't make. And in some cases, they simply have bugs, and so they have often given spectacularly wrong answers. So what about our proof assistants? I should say, and I seem to have not put it on my slide, our proof assistants are very carefully architected to minimize this, if you like, the code that you have to trust. But we can't expect mathematicians to believe us. So we have to look for other ways of building trust. And then there's this question of, okay, we defined division by 0 to equal 0. If you're wondering why, incidentally, if you look at a lot of the common laws governing division, you'll find that a lot of them continue to hold even if the divisors are 0. And that certainly makes our life very easy, so we can use these laws unconditionally rather than proving things to be non-zero. It's very pleasant. But I think when some mathematicians, when they see this, they this is like finding a dead body in the room for them. And then you have to get into an elaborate argument about how, well, you're not really talking about division anymore. You're talking about a function that coincides with division, except when the divisor is 0, which is a case you don't even care about anyway. So like, what is your problem? But you can imagine there will be an issue of trust here, that mathematicians will not want to believe the system. So I would just like to make a little plug here for structured proofs. So if you like, I have been in all of these talks pushing the system that I prefer, which is Isabelle. And one of the advantages of Isabelle is that it has this structured proof language, which I showed you at least one little example of, and which in general, you do have a good hope of reading a structured proof, even if you're not really trained. So what does this imply? Well, this little text exchange is one possible scenario. So the mathematician says, why should I trust it? And you say, we have architected our system with a small trusted kernel. And then he said, well, you've still got 1,000 lines of code that I can't read at all. And then you say, oh, well, we verified that code. We used our own system to verify the code. And then, first of all, he said, I don't trust your system. So I don't trust your proof either, because you did it in your system, which I already didn't trust. That's number one. Plus, your proof, what you call a proof, is just this horrible block of code that I can't read. So we on our side have done our very best to convince the mathematician, but we failed, right? So what is an alternative? The alternative is to say, look, here, you read the proof yourself. And now a mathematician is likely to say, good God, because believe me, that the level of detail we have to give is immense by their standards. And they're going to say, are you kidding me? So you had to prove, first, you prove that this function was continuous, then you prove something about its derivative, then you prove that, I mean, these are all incredibly obvious. Like, what is wrong with you? I said, well, I'm very sorry, but our system is not that clever. So at least then the mathematician will believe the proof, although of course he will not be impressed anymore because it's trivial. But this at least is the trust story that we can do. Now we do have the small trusted kernel, and some people, they are verifying parts of the kernel, but we don't need a mathematician to believe that, because we would like them to be able to read the actual formal proof object and recognize it as being a proof in its own right. Okay, so what is happening now? Well, as I said, research world is incredibly active. Loads and loads of things are being proved by everybody. It's really a very exciting time to be working here. And I want to say there's a lot of machine learning work being done now. Because we have tons and tons of formalized proofs, there are a lot of exciting possibilities around the lines of finding similar proofs. So you could imagine that you are working on your own proof and the system could pop up kind of like a better version of the Microsoft Word paperclip and say, did you know there's a very similar proof in the library over here? And in that proof, the next thing they did was this. So one could imagine doing that. So it kind of online hints coming from a machine learning driven thing that will use the knowledge of previous users to help us to extend our own proof. Now, there are some purely scientific questions that we are looking at now. So I really think, and of course, the question of simple type theory versus dependent type theory is one of the most fundamental scientific issues here. Now, of course, the people on the dependent type theory side, I know, in fact, I've known for 40 years, they are quite convinced that theirs is the only way. Now, clearly theirs is a viable way. They have certainly proved that with the work they've done. Whether it is the best way, I think, has not been proved. And this is, to my mind, one of the most interesting scientific questions. But also, for both of our formalisms, for the simply typed and the dependently typed one, we are still exploring the right way to use these formalisms to formalize the most advanced mathematics. And again, I would like to finish with a quotation, and this time it's Gödel. So that's all I have, and I'd like to take any questions now on either talk.
Is there any question?
So thank you very much. That was great. So you kept saying that that there's this problem that arises where obvious proofs, things that are obvious take huge amounts of time to verify in these systems.
Yes.
I mean, do you think that maybe that's not a problem, right? I mean, maybe this is somehow something that needs to be done. I mean, maybe these things that are obvious to mathematicians need to be checked somehow.
Well, I do like to say the obvious is not always true.
Yeah.
And I remember now, in fact, the reason I mentioned the problem of squaring the square, oh dear, I'm forgetting the details now. It was in a book by somebody very famous like Littlewood. So Littlewood wrote a mathematician's miscellany, I think. And then another mathematician, I forget his name, kind of reissued a mathematician's miscellany with, I think, annotations and corrections. And he corrected some errors that Littlewood had made. So that's just another example of the errors. And there are many examples where people have made mistakes. Nevertheless, a lot of the obvious stuff is really not difficult. It would be nice if you like to have something that could check the obvious things quickly and also tell us the things that were in fact false. It would be a wonderful thing to have. What's also odd is that some non-obvious things can be proved very quickly and automatically. So if you like, the automation that we possess is now extremely powerful, but it's kind of totally not comparable with human intuition. So things that mathematicians feel need to be spelled out in detail often can be proved fully automatically. And then other things that are too obvious to mention need hundreds of lines to formalize.
That's so. Is there much work being done? So there are some very controversial things. Is there a lot of work trying to check some of these proofs? So I'm thinking of like the ABC conjecture, or maybe that's not even controversial. Maybe people just think that the proof is false, right? I mean, is there some work to try and?
I'm not aware. I suspect that is too difficult now. Now there is a thing. What is it? What was it? The graph isomorphism problem and the claimed quasi-polynomial algorithm for it.
By Grow in Germany, right?
Something like that.
Right. Yeah. Okay.
I don't remember the guy's name. there are, I think, a fair number of these things out there that have been published, or that maybe they have been kind of mooted but not accepted. We're not quite at a stage to do this, I think. So it's funny, when I formalized Gödel's second incompleteness theorem, it was just an offhand remark by a logician I met at a workshop who said, you know, formalizing mathematics is all very well, but I believe that thing you formalized, but, you know, Gödel's second incompleteness theorem is awfully messy. And it is awfully messy, in fact. And yet there is I don't think anyone out there disbelieved it.
Is there any other question?
Yeah, hi, Lawrence.
Yeah.
Thanks so much for your talk. Yes, I have a question about the application of this automated theorem prover, because in the context of AI, I think we sometimes reason about the incomplete information. So this kinds of theorem prover is not very good for this. So I also talked with Professor Christoph. He used the higher order logic as a prover that can embed all the normative reasoning system, and such that these kinds of incomplete information can be handled by the higher order logic prover. So do you think it is that's one way to do this, or we can also use this higher order logic prover to implement the reasoning about the incomplete information?
I'm not quite sure in this case what you mean by incomplete information, and would this be a kind of heuristic assumption, or is it simply doing without certain information?
Yeah, it's just like the incomplete information means that there could be some exceptions. In this case, then some conflict will arise. So I think there are some other logical programming system like other set programming. So they use some kinds of means that the negation as failure. So they use this in a system, and then to make it possible to model the incomplete information. And then
I'm afraid that's not a thing I can answer. No, I don't know the answer to that.
Okay, so I think that could be not in the same direction, right?
Well, if you mean Christoph Benzmüller, I'm certainly sure he knows what he's talking about here.
Yeah.
If he can do it.
That, yes.
But I can't answer that, I'm sorry.
Okay, sorry. Okay, that's nice. And another question is, what is the role of this automatic theorem proving in artificial intelligence at the new period of time? Like now we in a field of machine learning, can we have some connection to the application? So you also mentioned machine learning, and you can use this theorem prover.
Well, I think the application of formalized mathematics is to mathematicians themselves. But as for machine learning, it's an interesting research area. It's very different from other applications of machine learning because normally machine learning is applied to things that are not precise. So you buy a book and machine learning tells you another book you might want to buy. Or maybe you, let's say you have some kind of electronic device that let's say like an Apple Watch, it has sensors, and if it detects something that seems like a fall, it decides that maybe you fell. It asks, did you fall? And that might be based on machine learning and based on a combination of things. But you know, if you didn't fall, that's fine. Nothing, no harm happened. In mathematics, things are absolutely precise. So if you use machine learning here, it's a more speculative use of machine learning that we are hoping that because a particular combination of primitives, say, was used in other proofs, and then a certain particular theorem was then used to continue the proof, then we are hoping that that theorem will be useful for the current proof as well. But that is different from recommending a book or a movie you might want to watch, because the question of whether you like a movie is not at all concrete or objective, whereas the question of whether a theorem is relevant or not, of course, is. So we can't be certain how valuable machine learning will be here. It is, at the moment, it is research. I mean, I think it will be of some value, but it is not a thing we can claim at the moment.
But you'd only be using machine learning for automated theorem proving, right, rather than verification of known results, right?
Yeah, my personal view is I don't really trust machine learning. So yeah. I think I'm totally happy with it recommending a book or a movie. I don't want it sort of driving a car all by itself.
Okay.
Yeah, absolutely.
I ask this question because now I am working in the direction of logic in artificial intelligence. So I hope that all our work can have some connection to some application in artificial intelligence. So because most of our reasoning is some kind of the human reasoning. So, but mathematical reasoning is very different from the human reasoning. So I just wondering whether this kind of work has some connection to the model of human reasoning, and then that can be better applied.
Well, I can't comment very much on human reasoning, except to say it certainly works, as you say, very differently from machine reasoning. And I know some people have wanted to apply theorem proving to machine learning. So they want to verify machine learning algorithms and so on. I'm not sure how useful that is. What could be useful, though this is taking us way off the topic of the talk here, but never mind. One could imagine the design of a system like a self-driving car, incorporating some machine learning, but also incorporating safety mechanisms to protect the passengers of the car from the errors of machine learning. In other words, you would want to prove the correctness of an overall system design that was not only machine learning. And I think things like that will be necessary if we put machine learning into systems that we rely on. I'm not sure that's relevant to your question, but I hope it's interesting.
Yes. Yes, my question, I think maybe I have not expressed very clearly because in artificial intelligence, there are some problems of the reasoning that is under open context. So there are some old problems like qualification or the frame problem. I think this kind of problem are very old. So I think this may have no relation to the theorem prover you've introduced today. So I think my main concern is about these kinds of things. So I don't know whether there is any connection between your work and also the work in the
Yes,
articulation.
probably not.
Yeah. Okay. So thanks a lot for this.
I think basically the mathematics, there's no way to handle exception, or there's no exception in mathematics, so to say. Right? I mean, it's the theorem always is a sound. It's sound, so there's no exception at all. Do you agree?
If it's correct.
Mm-hmm. Yeah, it must be correct in all cases.
Yeah.
Yes.
Is there any questions?
Do I have time to ask one more question, or is it? Laura, am I detaining you? Sorry. That's what's the is there what's the what I wanted to get an idea of was so ACL2, right?
Yeah.
Have I got that right?
Yeah.
That's based on something really, really weak, isn't it? Like,
did you say weak or weird?
Weak.
Weak, yes, weak. And a little weird, perhaps.
Okay. But is there, so that, I mean, that to some extent, I mean, there's an advantage to doing something, to having your base formalism very, very weak, right? I mean, that is some way of, that must be considered an advantage. Is that considered an advantage?
Well, ACL2 is extremely good at a niche area. They've applied it where, I mean, it's a very cool system. It has as its logical formalism a programming language, which is actually executable, which possibly Lean is doing the same thing, actually. But in ACL2, every formula is executable. So this is an example of a logic where you have, in fact, a constructive logic because everything can be evaluated, and yet the excluded middle actually holds because everything is computational, everything is decidable. And so they can, in particular, they specify hardware designs, and they can even run them, they can simulate them, and they can run them very efficiently. So for their application areas, it works very well. Drawbacks, though, I think they don't have the notion of a real number at all. So real numbers are not computational. I think they do some very clever thing with like non-standard rationals or something very, very weird to get something that is a little bit like the real numbers, but it's not a thing that you would want. I mean, you couldn't do analysis there, for example.
Okay. So I mean, I suppose that what I'm getting at is when you're looking for the right system, I mean, maybe logical strength is not really the kind of, you're not paying too much attention to logical strength. Are you more interested in how well it's able to formalize the objects you're talking about?
Yeah, there are. Yeah, it's an awful tangle at the moment. Maybe things will be clearer in 50 years.
Okay.
But yes, now the funny thing is, so you can attach set theory to higher order logic, Zermelo-Fraenkel axioms to higher order logic quite easily. And it doesn't even have to be as ugly as you might imagine it would be. And then you get a thing, of course, which is, I think, slightly stronger than ZFC. If you then want to do that kind of work, like the ordinal partition stuff, I had to use, I needed ZFC for that. But normally, so most people do not use this ZF extension. They don't need it. And it's really interesting how much even modern day mathematics you can do in this very weak system that's weaker than the Zermelo set theory.
Yeah, thank you very much.
Okay, thank you for the invitation.
Thank you, Lawrence. And
Thank you,
I really
Laura.
like your talk. I really like your talk.
I'm glad. Thank you very much indeed.
Yes. So let's keep in touch, and if you get any new results, you can always give us a talk.
Be happy to. Okay.
Yes. Okay. So wish you a good nice the weekend is almost there. So
Okay.
yes. Have a nice day also. Have a nice weekend.
Wednesday, isn't
Okay.
it?
Thank you.
Yes.
Wednesday.
I should
Almost
probably
weekend.
switch this off, right?
Good week.